Okay, moving on to the MCQ of halogen derivative tutorial. Right, so question 10. Alright, we're supposed to look at the product between 2-iodobutane and sodium ethoxide. Okay, so what's sodium ethoxide? Okay, sodium ethoxide is basically CH3CH2O minus and A plus. Okay, it's basically a reaction of your ethanol, right? CH3CH2OH losing a hydrogen, losing a proton, alright, to form, so it's a reaction between sodium, and you get this, your sodium ethoxide plus half H2 gas. Alright, this is a concept that we discussed in alcohols lecture. So you can see once you have the ethoxide is going to function as the nucleophile because there's a lone pair on the O and 2-iodobutane, CH3, CH2, C, then you have the I here, H, and then you have a CH3. You can see the iodine, it's on carbon number 2. So you have your delta plus, delta minus. So basically this reaction you're looking at, it's a nucleophilic substitution reaction. Okay, so in this case, the nucleophilic substitution reaction, the ethoxide will therefore replace the iodine. Okay, I repeat again, the ethoxide will replace the iodine. Okay, you substitute the iodine. Okay, so in this case, the question is not asking for SN1, SN2, it's just basically asking what's the product. So you can take a look at the option. Okay, so like I said, if you look at options, this is replacing the I. So this is the formula. Alright, so therefore the possible options when you look at it, A is wrong because A is elimination. Alright, then alkene. B is also wrong because the OCH3 is not correct. Okay. Then only option C looks like the correct one because if you were to do the matching, this is the ethoxide. Okay. And then you have a CH3 as attached to this CH, then CH2, CH3. Okay. That's why C is the correct option. And of course, D is the wrong option because D itself is not the correct structure. Okay, so the structure is that basically you attach O to this carbon, OCH2, CH3 to this carbon, so you get this product. Okay, CH3, CH2, CO, CH2, CH3, H, CH3. Okay, that's your question 10. Okay, moving forward, we're going to go to question 11. In question 11, compound X is a chloroalkane of molecular formula C7H15Cl. Undergoes a hydrolysis when warmed with excess aqueous sodium hydroxide. When the reaction is complete, the major organic product forms a racemic mixture. So recall, it's racemic mixture meaning that you must have chiral carbon and equal amount of each enantiomer. Okay, and recall what kind of halogenal alkanes give a racemic mixture. It must undergo SN1 type of reaction. Okay, so if you take a look at option A is obviously wrong because option A is a primary halogenal alkane. A primary halogenal alkane will not undergo SN1. Okay, then leaving possibly B, C, and D, of which all of them are tertiary halogenal alkane. Okay, so that's, of course, when you look at my solution, I already have done the pre-processing. To determine whether it's primary, secondary, tertiary, my advice to all of you is to consider drawing out the structure, alright, because it's very difficult to interpret the structures from a one-liner structure like this. So, what do I mean by drawing out structure? So you can see I can have CH3, CH2, then C, then I have CH2, CH3, because I have 3 of them, right? 3 ethyl groups, CH2, CH3, and that's how I can see that it's a tertiary halogenal alkane. Okay, for B, that's option B. And then for option C, you have CH3, 2 of them, and CH, CH3, and CH2, C, Cl, with 2 CH3 group. Okay, so you need to physically draw out, alright, to see that this is a tertiary, again, tertiary halogen alkane because there's 3 R groups, 1 R group here, 2 R group, and 3 R group. So it's again tertiary. Okay, but more importantly, alright, you realize that for this B and C, you do not have any chiral carbon. Because why? In this case, there's no chiral carbon because this carbon here is connected to 3 similar groups. This carbon here there's 2 similar identical CH3 group. Only option D has a chiral carbon. So take a look at CH3, 2 of them, then CH, followed by C, CH3, CH2, CH3, and then the Cl. So you have a chiral carbon over here. And because you have a chiral carbon, after the OH hydrolysis, right, when you use sodium hydroxide, alright, when you replace the sodium hydroxide, replace the Cl with a OH, and then you still have a chiral carbon, and that's where you have a racemic mixture. Okay, so you must have a chiral carbon in the end of the reaction. So therefore, that's the only way you can have a racemic mixture, because you need to first form enantiomers. Okay, so that's why the answer is therefore D. Okay. Okay, moving on. The use of data book is relevant to this question. So we have 2 bromopropane react with the following. So 2 bromopropane is this structure over here, Br. When it reacts with sodium hydroxide, it will form compound P. So recall sodium hydroxide with halogen alkane, what kind of reaction? It's slightly equals, right? So it's going to be a OH. Alcoholic solution is an elimination reaction, so you get a propene, that's a Q, so PQ. And the sodium cyanide is alcoholic, so you're doing a CN. So in this case, we are supposed to look at the products and rank the highest, lowest to highest. So of course, Q will be the lowest, then R will be the highest. So Q lowest, R the highest. Just calculate MR, right? And therefore, Q smaller than P, smaller than R. Answer will be B. Okay, so you just have to calculate the MR. So it's quite obvious. When you do elimination, definitely the MR will be the smallest. I don't have to physically calculate out. Alright, because you're losing atoms, alright, from the original molecule, so therefore the MR will be the lowest. Then comparing CN and OH, CN of course has a higher MR than OH, and that's why R will be the highest. Okay, so in this case, there's no need for you to physically calculate MR. But of course, if you want to, you can, like as shown in these solutions over here. But it's really a waste of time. So for MCQ, you need to optimize your time. Okay, moving on. Question 13. Okay, bromo-18 is very unreactive to nucleophile, whereas 3-bromopropane is very reactive by comparison. Again, in this case, we have a halogenal alkene versus a halogenal alkane. This Br is connected to CH2, which is a sp3 carbon. Okay, so this is a halogenal alkane, this is a halogenal alkene. A and E. So look at the difference. So why is a halogenal alkene unreactive? That's the question. So electrons of bromine atom delocalize in the pi bond. Yes, that's correct, because this strengthens the CBr bond, and you have a partial double bond character, which makes nucleophilic substitution very difficult. The electrons of the pi bonds repel the attacking nucleophile. That's correct. Alright, the pi bond. So imagine if I have a halogenal alkene, in this case, this compound here, my delta plus carbon is here, but I have my pi electron clouds here, which means that my nucleophile cannot attack this carbon because the pi electron clouds repel the nucleophile, which is electron rich. Okay, so therefore it will stop. It will not be able to attack the delta plus carbon. Okay. The presence of the pi bond prevents free rotation of the CBr bond. That's wrong, because the CBr bond is still free rotating. Why is it a free rotating CBr bond? The one that restricts rotation is the carbon-carbon bond. The CBr bond is a single bond. There's no rotation on that. So that's why option 3 is wrong. So option 1 and 2 are correct, and therefore answer is B. Okay. Question 14. Okay, which of the chloroalkanes with formula C5H11 gives the largest number of isomeric products when heated with ethanoic potassium hydroxide? So when you look at heated with ethanoic potassium hydroxide, we are looking at elimination. So elimination, recall, I look at the CX, I need to look for adjacent carbons with hydrogen. So there are multiple ways to remove. You need to consider all possible ways. Now let's take a look at option A then. Option A, the chloro is at carbon number 1 on the adjacent carbon. So this is carbon number 1, right? On the adjacent carbon, this is the only adjacent carbon. Alright, this is the one that highlighted in yellow is the only adjacent carbon. So there's only one way to eliminate, and therefore there's only one alkene. This alkene is a terminal alkene, and as a result, there's no cis-trans isomerism. There's total 1 isomeric alkene products. So after figuring out how to do this, alright, you can pause this video if you have troubles getting the correct answer. Alright, you basically try to see how many different alkenes you can get from B, C, and D, and you compare. Okay, so for B itself, this is the carbon that has your alkene. Okay, this is a carbon that has your alkene. Okay, so the adjacent carbon, adjacent means directly next to it, right? Is this carbon here. Now, if you look at this adjacent carbon, there is no hydrogen attached to this adjacent carbon. Okay, there's no hydrogen attached to the yellow carbon on B, which means elimination is not possible. Okay, therefore B will not give any alkenes. Okay, moving on to C. C itself, this is the carbon which is Cl. The two adjacent carbons are here and here. So there are two ways you can eliminate. Either you eliminate this way or you eliminate this way. So the double bonds can be either between these two carbons or between these two carbons. So let's take a look at the alkenes. What are possible ones you can form. You have a terminal alkene. If I eliminate the blue way, I get a terminal alkene. Alright. In this case, there's no cis-trans because terminal alkene cannot exhibit cis-trans. Or I can have an alkene that looks like this, where the double bond is between these two carbons. Alright, in this case, you notice that these carbons that form the CC double bond, each has two different groups. Alright, each has two different groups. This first carbon here, alright, let's just call carbon A, carbon B. Carbon A has a H and a CH3. Carbon B has a H and a CH2, CH3. So there are two different groups on each carbon of the CC double bond. And that's why cis-trans is possible. So you therefore have cis and trans. In total, you have 1, 2, and 3, and therefore 3 isomeric alkenes. Okay? Is that the most? Let's take a look at D then. D itself, this is the carbon with your halogen. There are 3 adjacent carbon with hydrogens. Okay? But take note, these two methyl groups are the same. Because no matter how you eliminate, you will get a terminal alkene. Alright, so essentially, you eliminate this way or this way, it's going to be the same. So therefore, there's only 2 alkenes that's possible, either via the red hydrogens or remove the hydrogen here with the CC double bond between the green carbon as circled and the green highlighted carbon. Okay, so there are only 2 alkenes, and then we just have to check whether they're cis-trans. So for the terminal alkene, alright, eliminate via the red way, the CC double bond between here, right? There is not going to be any cis-trans because any terminal alkene cannot exhibit cis-trans because this carbon has the two of the same substituent. In the other case, over here, you cannot have cis-trans also if you have double bond between, if I eliminate the green way, alright, this carbon that's highlighted in green will have 2 CH3 group again, which is of the same group, and therefore there's no cis-trans. And therefore, there's only a total of 2 isomeric alkenes, and therefore option C gives rise to the most number of alkenes. So therefore, C is the correct answer. Okay? With that, I'm done with the MCQ.